Dear students, welcome back. In this class, let us discuss about a new term. It is lattice point. What is a lattice? Lattice point means, it is lattice point. Lattice point means, a point is said to be lattice point. It is with the integer coordinates. Lattice point is a point with the integer coordinates. Means consider, consider this point 1 and 2. So this is a lattice point. Why? Because this point, suppose A be the point, then A has integer coordinates 1 and 2. Similarly, you can find out infinite number of lattice points. Means lattice point is a point with the integer coordinates. Then, suppose P and Q are any two points. Then this P and Q are said to be mutually visible. The two lattice points P and Q are said to be mutually visible if the line segments which join these points P and Q contains no lattice point other than this endpoints P and Q. Means you consider this point 1 and 2, so it is 2, 3. Then it is 1 and 2, and consider this point, or let ordered pair 1, 2 is a point, and 1, 2. So suppose ordered pair 2, 3 is another point. Let it be P and this Q. Then consider this PQ. The line segment PQ consists of no other lattice points except the endpoints P and Q itself. So this P and Q are said to be mutually visible. The two lattice points P and Q are said to be mutually visible only if the line segment join this P and Q contains no other lattice points except this P and Q. Agree? Now, if the 2 points ordered pair AB and ordered pair MN are mutually visible, if and only if, then A minus M, B minus N are relatively primes to each other. A minus M and B minus N are relatively primes to each other. If A and AB, ordered pair AB and ordered pair MN are mutually visible, if and only if A minus M, B minus N are relatively primes to each other. Agree? So this is the definition of a lattice point. Lattice point means a point with the integer coordinates. Now, come to your research. The set of lattice points in a plane visible from the origin, that is visible from the origin, contains arbitrarily large square gaps. That is, given any positive integer k, there exists a lattice point ordered pair AB. There exists a lattice point ordered pair AB such that none of the lattice points A plus R, B plus S. A plus R, B plus S is again a lattice point. A plus R, B plus S, where 0 less than or equals R less than or equals K and 0 less than or equals S less than or equals K is visible from the origin. For any positive integer k, there exists a ordered pair AB, that is a lattice point, such that none of the lattice points ordered pair A plus R, B plus S, where R and S are ranges from 0 to k, is visible from the origin. Means to consider what is the origin, and suppose this is the point E, and this is A plus 1, etc., and this is A plus 1, so this point is A plus k. Okay. This is the point B, then it is B plus 1, etc. This is B plus k. So A plus k, B plus k. Means consider this one. So this is ordered pair AB, this is ordered pair A plus KB. Okay. Then consider this one. So this is A plus k and A. So what about this point? This point is A plus k, B plus k, and this point is ordered pair AB. There are number of such points. So this is ordered pair AB, and that opposite corner is ordered by A plus K, B plus K. Let P1, P2, its proof is in this way. Consider the proof. Let P1, P2, etc. Pk, let P1, P2, etc. Pk be the square of primes. Pk be the square of primes. Let epsilon is positive. Consider the K by K matrix. There is a K by K matrix whose entries in the first row consist first K primes. Means consider a 2 by 2 matrix. So the first row consists the first 2 primes. Second row consists of the next 2 primes. So consider a 2 by 2 matrix. The first row consists of first 2 primes. The second row consists of next 2 primes, and so on. So like this, let's consider a K by K matrix whose first row consists of first K primes, second row consists of next K primes, and so on. And let Mi be the product of primes in the ith row, and capital Mi be the product of primes in the ith column. Listen, here M1 be the product of primes in the first row. Here M1, what is M1? M1 is 6. M2 be the product of primes in the second column, that is 35. Capital M1 be the product of primes in the first column, that is 10. M2, capital M2 be the product of primes in the second column, that is 21. So like this, M may be the product of primes in ith row, and capital M may be the product of primes in ith column. Clearly these MIs are relatively prime. Why? Because all the elements in each rows are primes. So MIs are relatively primes, means they are prime in pairs. Similarly, capital M is also prime in pairs. Agreed. So now consider the congruences. The congruence relations: x congruence to minus 1 mod m1, x congruence to minus 1 mod m1, and etc. x congruence to minus 1 mod mr, where r 0 less than or equals r less than or equals k. But what about these small mi's m1, m2, m3, etc. mr? These small mi's are relatively prime in pairs. Therefore, by Chinese remainder theorem, the system x congruence to 1 mod m1, minus 1 mod m1, etc. x congruence to minus 1 mod mr has unique solution modulo m1, m2, etc. m1. Let A be the solution. Let A be the solution of this system modulo. Let A be the solution of this system modulo m1. That is, A be the solution of this system modulo mr means A congruence to minus r mod, A congruence to minus r mod m1. Okay. Similarly, consider y congruence to minus 1 mod m1, etc. y congruence to minus 1 mod mr, capital M1, etc. capital mr. Agreed. Since each mi's are relatively prime in pairs, therefore this system, consider this system 1 and system 2. This system also has a unique solution modulo capital M1, M2, etc. capital M1, M2, etc. ms. That means let B be the solution. So B congruence to minus S mod ms. So that means A congruence to minus R mod mr means small mr divides A plus R. Similarly, this gives capital MS divides B plus S. Agreed. MR divides A plus R and MS divides B plus S. Therefore, there is a prime in the intersection of rth row and mth column will divide A plus R and B plus S. What is MR? MR be the product of primes in rth row, and capital MS be the product of primes in sth column. Means the product of primes or the primes in the intersection of this rth row and sth column will be divided A plus R and M plus S. So A plus R and M plus B plus S. A plus R and B plus S. That means this A plus R and B plus S are not relatively prime. That's a contradiction to the hypothesis A plus R and B plus S are lattice points, and they are lattice points, then therefore it does not visible from the origin. Okay, so this is the proof. Clear? So now let us consider a problem. Find all positive integers n. Find all positive integers n for which n power 13 is congruent to n mod n power 13 is congruent to n mod 1365. Find all the positive integers n such that n power 13 congruent to n mod 1365. How? First you factorize this 1365 into prime factors. Means, so it is n power 13 is congruent to n mod. What is 1365? 1365 is nothing but it is 3 into 5 into 7 into 30. You can factorize this 1365 into the product of primes. 3, 5, 7. 3 into 5 into 7 into 13 is nothing but 1365. So n power 13 is congruent to n mod 3 into 5 into 7 into 30. We have to, in order to solve n power 13 congruent to n mod 1365, we have to solve n power 13 is congruent to n mod 3, 5, 7 and 30. We have to solve n power 13 congruent to n mod 3, n power 13 congruent to n mod 5, n power 13 congruent to n mod 7 and n power 13 congruent to n mod 30. How this one? So we can consider this 3. If 3 does not divide n, then we have already proved a theorem. If p does not divide a, then a power p minus 1 congruent to 1 mod p. Agreed? So according to that argument, if 3 does not divide n, then n power 3 minus 1, that implies n power 3 minus 1, a power p minus 1, n power 3 minus 1 is congruent to 1 mod 3. N power 3 minus 1 means n square. So n square congruent to 1 mod 3. Agreed? N square congruent to 1 mod 3 means n square all power 6. N square all power 6 congruent to 1 power 6 mod 3. Okay? That means n power 12 congruent to 1 mod 3. That means n power 13 congruent to 1 mod 3. Sure? If 3 divides c, what happens? This is the second case. If 3 divides c. So the little Fermat theorem states, if p divides a, then a power p congruent to a mod p. If p divides a, then a power p congruent to a mod p. If 3 divides n, we have, yes, n cube congruent to 1 mod 3. Agreed? So n power, if 3 divides n, then clearly n cube congruent to 1 mod 3. That means yes, n cube all power 4 congruent to 1 mod 3. That means n power 13 congruent to n mod 3. Okay. So when 3 does not divide Cn, we show that n cube congruent to n mod 3, as well as when 3 divides Cn, n cube also congruent to n mod 3. Similarly, now you consider 5. If 5 does not divide Cn, surely n power 5 minus 1 means n power 4 congruent to 1 mod 5. Means n power 4 whole cube, that is n power 12. So n power 12 congruent to 1 mod 5. Means it is n power 13 congruent to n mod 5. If 5 divides Cn, then by little Fermat theorem, n power 5 congruent to n power 5 also congruence to, or a power p congruence to a mod p. So if 5 divides n, then n power 5 13 also congruence to, yes, if n power 13 congruence to n mod, n power 13 congruence to n mod 5. Similarly, if 3 does not divide 7, again, if 3 does not divide, 7 does not divide Cn. If 7 does not divide Cn, again n power 7 minus 1 means n power 6 congruence to 1 mod of 7, that is n power 7 minus 1 means n power 6 congruence to 1 mod 7, that means n power 13 congruence to n mod 7. Agree? If 7 divides n, immediately n power 13 congruence to n mod 7. That's immediate. If 7 divides n, then n is a multiple of 7, n power 13 is also a multiple of 7, so it is n power 13 is also congruence to n mod 7. That's immediate. Similarly, if 13 does not divide Cn, n power 12 congruence to 1 mod 13, that is n cube congruence to 1 mod n mod 13. If 13 divides Cn, then surely n power 13 congruence to n mod 13. Therefore, find all the positive integers n which satisfies this relation. So the positive integers are 3, 5, 7 and 10. Okay. Now come to the next problem. Find all the positive integers n such that n cube, not n cube, it is, find all the positive integers such that n power 17 is congruence to, n power 17 congruence to n mod 4080, n mod 4080. Find all the positive integers n such that n power 17 congruence to n mod 4080. First you can factorize this 4080. What is 4080? 4080 can be factorized as by the least prime 2 if you divide it with the least prime 2 and so on. So it is 2 power 4. 2 power 4 into 3 into 5 into 3 into 5 into 70. Okay. 2 power 4 means 60. Then as in the previous case, if 3 does not divide Cn, then n power 3 minus 1 means n square congruence to 1 mod 3. So in order to find out the odd integers n power 7 congruence to n mod 4080, then it is congruence to n mod 2 power 4, n mod 3, n mod 5, n mod 70. So if 3 does not divide Cn, then n square congruence to 1 mod 3, surely n square all power 16 also congruence to n power 16. n power 16 congruence to 1 mod 3. If you take 8th power, that means n power 17 congruence to n mod 3. Okay. If 3 divides Cn, what happens? According to the Little Fermat theorem, it is n power 17 congruence to n mod 3. Enough. Similarly, in the case 5 and 17, if 5 does not divide Cn, then n power 4. n power 4 congruence to 1 mod 5 and so on. If similarly, if 5 does not divide Cn, n power 4 congruence to 1 mod 5, therefore n power 16 congruence to 1 mod 5, n power 17 congruence to n mod 5. If 5 divides Cn, n power 17 congruence to n mod 5. Similarly, 17 does not divide Cn, n power 16 congruence to 1 mod 17, therefore n power 16 congruence to n mod 17 and so on. Now what remains? 2 power 4. That's 2 power 4. Suppose n is odd. Therefore, means n power here according to, here we can put n power 17 minus n is divisible by 3 into 5 into 70. Okay. From these arguments, we can say that n power 17 is congruence to n mod 3, 5, 7 means 3 into 5 into 17. That is n power 7 minus n is divisible by 3 into 5 into 7. Now consider, suppose n is odd. N is odd means n equals some to k plus 1. N equals to k plus 1. So what about n power 16? N power 16 is equals, n power 16 equals 2k plus 1 all power 16. Okay, 2k plus 1 all power 16. 2k plus 1 all power 16 means, according to binomial theorem, it is 1 plus, that is 1 plus 2k all power 16. So it is 1 plus 16 into 2k plus 16c2 into 2k whole square plus etc. plus 2k all power 16. Okay, that means it is 1 plus multiple of 16. Okay, yes. So it is n power 16 is congruent to n power 16 is equals 1 plus multiple of 16. That means n power 16 congruent to 1 mod 16. That means n power 17 congruent to n mod 16. N mod, yes, n power 17 congruent to n mod 16. Sorry, not 17, n mod 16. Okay. Now, if n is even, n equals some 2k. If n is even means n equals 2k. N is even, or when n is even, yes, n is even. What is n power 16? N power 16 is also even. Let's immediate. N power 16 is even means n power 16 minus 1 is odd. N power 16 minus 1 is odd. N power 16 minus when n is odd, surely n power 17 minus n is multiple of 16. So when n power 16 minus 1 is odd, surely n into n power 16 minus 1 is divisible by n into n power 16 minus 1 is divisible by 16. That means n power 17 congruent to n mod 16. Therefore, n power 17 minus n is divisible by 3 into 5 into 17 into 16. So these are the integrals. Agreed? Okay. So now this third chapter is also over. So first module is also over. Now in the next class, let us discuss second module. Thank you.